Hello, today we're going to do our first lab, iodination of vanillin. This is an experiment that we do in the second semester organic chemistry course. This lab's going to use green chemistry techniques. What that means is using very low toxic solvents like water or ethanol in this case, and things that are very commonly found around the house like bleach. Okay. So it doesn't use anything special, very tremendously toxic. Now, the vanillin, it smells nice, but it can still cause toxicity. We know vanillin is used as a flavoring agent in cooking, in candles, ice cream. It's found in coffee too, if you add that to your coffee. Electrophilic aromatic substitution is something we learn about in organic chemistry. And remember that the mechanism always involves two steps. So you have some kind of aromatic ring. Here we'll just use benzene as the typical nucleophile. And then we have some electrophile that's present. And we take the pi bonding electrons in this aromatic system and attack the electrophile. Okay. And this gives us a carbocation intermediate that is super resonance stabilized because of two pi bonds that are in conjugation with that. So I won't draw all the resonance structures here for the carbocation, but you should be familiar and comfortable doing that. Now, this intermediate here loses, so that's A for attack, all right? In the first step, and then there's loss of a proton. This is very acidic. It's desperate to lose a proton to re-aromatize, and so some solvent, okay, in solution acts as the base, right? So there's our lone pairs, and this is going to deprotonate and give us the substituted product. Okay. So we are substituting this hydrogen for this group, and we want to iodinate the ring, okay? So the driving mechanism for this reaction is stabilization of the intermediate, okay? And of course, the bonds in the product must be stronger than the bonds in the starting material, so that drives the equilibrium to the right. Now we've learned about electron donating groups, how the OH group is a strong electron donating group. Okay. And hydroxyl groups are strong electron donating groups, which mean they accelerate the reaction, they make it faster. Okay. They activate the aromatic ring. Okay. Activation means that the aromatic ring is more nucleophilic, more reactive, more likely to react with the electrophile in solution. Now, iodination typically requires a coactivator like copper 2 chloride or other inorganic metals to create a very powerful electrophile in solution, and then that reacts with the aromatic substituent. Now, vanillin already has two activating groups on the ring. Okay, so this is the structure of vanillin, and you can see how this group right here is an activator. It's an ortho-para director. So we'll use boxes to indicate where we are directing. We're directing to the ortho position here, okay? Now, the OCH3 group is also a strong electron donating group, but not as strong as the OH group. And this guy here also directs ortho and para, okay? So the only ortho group possible that we could substitute is there, okay? So remember that the OH is a stronger director then OCH3. So if we add an electrophile to this system, we would expect electrophilic aromatic substitution to occur ortho to the hydroxyl group, ortho to the phenol at that yellow box to give us iodination Oops. Right there, okay? So I'll box that guy up. And I'll just write I plus, if you will. I'll put that in quotes so you know that that's not really in solution. So if we treat this with an electrophilic source of iodine, we would expect electrophilic aromatic substitution at that ortho position to the phenol, because the phenol is a stronger electron donating group, okay? You might expect a side product to occur where we have iodination ortho to the methoxy group, okay? That is possible. Now, in this lab, we're gonna use household bleach. Household bleach is chlorine, Cl2. If you smell it, you do smell the chlorine, but it's also in equilibrium with sodium hypochlorite. Hypochlorite ion is aqueous, and that's in solution, okay? Now, bleach is a strong oxidant, and that's going to be able to oxidize sodium iodide to form I2, or elemental iodine. Iodine is the electrophile that's going to react with vanillin, okay, and to give us the iodovanillin product, okay. Behind me, I have all the equipment necessary to do this lab and the chemical reagents necessary, okay. So we're going to be using ethanol, which is a non-toxic solvent, and vanillin, of course, comes as a solid powder. It's a white solid powder. And we have our beaker for our ice bath and our reaction flask here. And we have bleach. I don't know if this is 5.25% bleach, but bleach is used in excess in this chemical reaction. So, and here's sodium iodide. The sodium iodide becomes oxidized with bleach to form iodine, and you'll see a kind of a darker brown color when these two are mixed together. Sodium thiosulfate is necessary to reduce any excess bleach or any excess iodine present during the reaction mixture. Sodium thiosulfate will reduce those strong oxidants and neutralize the solution. Now, because of the basicity of the bleach, we want to neutralize the solution with hydrochloric acid. That's a solution of 3.2 molar hydrochloric acid, and that will bring the reaction to a nice neutral reaction mixture. Now, I just want to point out that phenols are acidic. Okay, so if we have vanillin here, and we treat this with basic bleach. Bleach is a base. If you spill some on your hands while you're doing laundry, you can feel that slipperiness in your fingers. And that's because there's basically a mixture of sodium hydroxide and chlorine, or sodium hypochlorite. Hypochlorite is a weak base. Now, this can deprotonate and form the phenoxide, in solution, okay? And that goes on to react with iodine to form iodovanillin. Now, because this is ionic, it's going to be water soluble, and we want this to precipitate out of solution so we can filter it. So that's why we add the hydrochloric acid at the very last step. This will protonate the phenoxide to give us the neutral phenol. And this neutral organic molecule does not have tremendous water solubility, so it can be filtered. When you buy vanilla extract at the store, it's in a solution of alcohol, okay? So if you look at the ingredients of your vanilla extract in the kitchen at your house, it'll say vanilla, either synthetic or natural, it'll say ethanol and then water, or it'll say alcohol or something like that. Now, it's not vodka, but there's a small amount of alcohol in there that can solubilize the vanillin. So that's why in the procedure, you will see me evaporate the ethanol from the solution, because ethanol and water can still dissolve this neutral vanillin molecule. So we need to evaporate the ethanol, and then it's really not very soluble in water. So then we can filter it, chill it on ice, filter it, and go from there in the analysis. So that's the introduction to the lab. Let me go ahead and do the lab now. Okay, for this lab, we fill out data sheets. These are available on Canvas. And watch while I do the experiment. I'll put different things in the balance, and you can record the masses. Now, for the accepted melting point of iodovanillin, there are two choices you can use for this. Since you're online, you can use chemspider.org. I will provide a link in this YouTube video to that. And you can draw the chemical structure or type the IUPAC name or the synonym even. It will give you a link, and it'll show you all the physical properties of that substance. And you want to find what the melting point is for this substance. Melting point is always a range. You can also sometimes find that on the bottle. We don't have iodovanillin in the lab, but I wanted to just show you how sometimes the melting point is on the bottle. It's not in this case, okay? Now, if you struggle with calculating the theoretical recovery of iodovanillin, that means the theoretical yield, you should watch the two introductory videos that I posted way back before the first day of the Organic Chemistry 1 lab. Okay, so review how to calculate theoretical yield. In this reaction, as I mentioned in the introductory video, vanillin is the limiting reactant. Vanillin is otherwise known as 4-hydroxy 3-methoxy benzaldehyde, okay? And you can use this formula weight or molar mass right off the bottle. It says 152.15. It gives you the molecular formula here, and it also gives you the chemical abstract service or CAS number. That can be used to determine toxicity. You'll find that this substance is not very toxic. A number 1 is very low toxicity. Okay, this is what I call the fresh symbol. Fire is in red. Reactivity is here. Safety is on the bottom if there's any special safety precautions, and reactivity. Okay, so fresh, fire, reactivity, safety, and health. So it's not very flammable. It's not very health. There's not problems with health. It's added to cookies, for example, but not as a pure solid, just as a dilute solution. On the back of this, we're on the second page, if you're online, there's some questions, right, that you should answer. And I addressed all of these questions in the introductory video. So watch that 10-minute video where I explain the reaction mechanism, why this, why that, why we add this, why we add that, how it works, what reaction's going on. So you should be able to answer all of these, okay? So the reaction of vanillin with all of these reagents. So first of all, in step 1, we have bleach, which is sodium hypochlorite that reacts with iodide or sodium iodide to form iodine, sodium chloride water. I won't balance this. It's a redox reaction, okay? So I'm just gonna use this in the next step. And we're doing organic chemistry, so we need to really pay attention to the organic chemistry part of the class. So let's show this reaction here. We have vanillin. Now I'm just gonna show neutral vanillin here, but probably it's deprotonated. So let's maybe just deprotonate it. Again, as I mentioned, bleach is a very basic substance because of the sodium hydroxide present. And so this is gonna deprotonate. I'll show the acid-base reaction there. So we have hydroxide present. That's gonna deprotonate. and make the phenoxide, okay? Now, as we'll see with aldehydes and ketones much later in the class, always use your lone pairs. So here's where I'm going to use iodine. Iodine has just a bond, single bond, and we're gonna take the lone pairs on oxygen here and attack the iodine molecule. Now you might be wondering, why don't I form the carbocation? Well, we have an O negative right next to the carbocation, so why don't we just, connect the negative and positive to make that double bond there? So that's what I'm doing. So in this reaction, this is the key step that produces that carbon iodine bond, all right? And then comes along some base. Remember, this is in basic reaction condition. Hypochlorite, hydroxide, something is gonna probably deprotonate. You could even use water, but I would use OH minus as the base, okay? And so this is kind of unique to our chemistry here because we're doing the reaction under basic conditions. Normally, electrophilic aromatic substitution reactions under acid. And that gives you the product there, okay? Well, almost the product. So the iodine goes ortho to the OH or the phenol or the phenoxide because it's a very strong electron donating group. It's got the negative charge. O minus is a tremendously good electron donating group. And then, of course, when we add hydrochloric acid, this is where the phenoxide becomes protonated, okay? And you form iodophenol, okay? All right. So my handwriting is a little bit sloppy there. Okay, so that right there is the molecule that we are suspecting to form. So I just wanted to show you the curved arrow reaction mechanism from start to finish in case you weren't sure about that. All right. So it's not required in the post-lab questions, but I just wanted to show you there. All right. So that's it. Now we'll start the lab. For the lab, we're going to be reacting our substances in this 100 milliliter round bottom flask. And these cork rings are pretty fancy. They hold them so they don't roll around the countertop. To stir the reaction, we'll be using this magnetic stir bar. It's a Teflon coated magnet, and within this stir plate is a motor with a magnet that causes this to stir around automatically. We're gonna add 1.00 grams of vanillin. We're going to add 20 milliliters of denatured alcohol. And we'll go ahead and clamp this in our ice bath and get it stirring. Okay. Now what we'll do is we'll add 1.17 grams of sodium iodide. Now the bleach I'm using is not 5.25%. it's 7.55%. So I had to do a little bit of math using the dilution formula, and I'm adding 6.5 milliliters of this bleach. So that's going to be equivalent to 11 milliliters of 5.25% bleach. I'm going to be doing the addition through this separatory funnel, and I'll just let that drip in a very controlled fashion. And I think I'll add just a little bit of water here just to make the volume about 11 milliliters in total. So I'm not adding bleach, this is just ice water here. I'm kind of diluting the bleach down a little bit. Okay. And I'll add this to my separatory funnel, and then by adjusting this valve here, I can drip it in slowly over the 10 minutes. Right now I'm waiting for the ice cold mixture of ethanol, vanillin, and sodium iodide to cool to 0 degrees Celsius before I start the dropwise addition of bleach. So we'll wait about 10 minutes and then we'll come back and then we'll start the addition of bleach. Okay, it's been about 10 minutes and our ethanol, vanillin, sodium iodide solution is nice and homogeneous and ice chilled. And we want to add this over about 10 minutes, 10-15 minutes would be good. And we just want to crack the valve just a little bit so that it very slowly dispenses into the solution here below. When the first drop hits, it's quite interesting because it's a dramatic color change. As you can see in the video, iodine is a dark reddish brown. All right, so drip, drip, drip. That's the rate at which I'm adding this. That might be more like 15 or 20 minutes. I'm not sure. We'll find out in the end. So there's about 11 milliliters up here. And yeah, so we just let the addition go. And presumably the iodine's being formed. And once the iodine is formed, that is going to be reacting with the aromatic ring through an electrophilic aromatic iodination reaction. So we'll let that go and then we'll come on to the next step later. The stirring has momentarily stopped here, so let me try to fix that. All right, the stir bar just kind of stopped. I noticed maybe some solid formation in the bottom of this guy here, so I'm just going to manually kind of shake it. The reason for the stopping of the stirring is the solid formation, and also it's about a couple inches away from the stir plate, so it doesn't really have a strong magnetic interaction with the stirring bar. So the reaction should still work. I'll just have to sit here and fiddle with the manual stirring. So let me restart the addition here, nice and slowly. And it's only been about 5 minutes so far, so we're about halfway there. All right, I managed to get the stir bar stirring again, so looks like we're back up to speed. And we've got a drip, so a little bit slower, but it's still being added dropwise. And the solution looks a little bit heterogeneous. There's a very small amount of solid in there, it looks like. But it's stirring and it's being added, so I guess we're good. I'll check on this periodically, but we'll just let this go. Okay, that's the last drop there. And just open this just to make sure. Shake it off. And that was about 13 minutes total time on the video, so I'm happy with that. You'll notice that the dark red color, perhaps maybe not visible on the camera, has lightened up a little bit. And now the procedure, there's quite a bit of solid formation in this flask, but the stir bar can still stir. The procedure now calls for us to stir this, warm this up to room temperature and stir it an additional 10 minutes. So let's go ahead and do that. And we're 14 minutes into the video here, so I'll go ahead and just let that go for another 10 minutes and come back and check in on it. All right, this has been approximately 10 minutes, and it feels cool to the touch, but it's not ice cold anymore. The reaction mixture hasn't changed that much, as you can see. The procedure, let's check this carefully. Next asks us to add about 1 milliliter of a 10% sodium thiosulfate. As you saw in my introductory video, this serves to reduce any iodine that might be left over from the chemical reaction. Since iodine is reddish brown, we should see the color dissipate. So that's 1 milliliter. And not sure if you can see it too well on the video, but the color has dissipated a little bit, okay? So that was the addition of 1 milliliter. Next, what we want to do is acidify the solution with 3.2 molar hydrochloric acid. That's 10% hydrochloric acid, by the way. And I'm going to use pH paper to check that it has an acidic pH. So we're looking for a light green, yellow, red, reddish hues, orange, any color up here would be acidic. But we don't want to overdo it and just dump in a ton. We just want to, you know, barely acidify the reaction mixture. Now right now, because bleach right here is basic, the phenol product and the phenol starting material are both deprotonated as the phenoxide, which make it water soluble to a very large extent. So when we add hydrochloric acid, we neutralize the phenoxide and make the neutral phenol, and that's going to have significantly less water solubility and ethanol solubility, so it's going to precipitate out. So let's go ahead and acidify this. So first off, let's check the pH, just to make sure the pH paper is working and we kind of know what to expect. Okay, so if I drop a bit of solution onto this pH paper, you can see that it reads pH, you know, maybe 8 or 9, fairly neutral. Okay, so it's a little bit not too basic. Now, we'll add this dropwise. And that was about 1 milliliter. So let's touch a hanging drop from the tip of our stirring rod onto this pH paper. And now it's changed to a lightish green kind of color there, okay? So I think that might be right around acidic, okay? pH 6 or so. I have some litmus paper. I forget the exact pH range that litmus paper works, but it doesn't work at 6.99. It's going to change red. It has to be significantly acidic to change it red, and I forget what that range is, 6.5 or 6 or something like that. Don't remember exactly, but litmus paper will change red if it's sufficiently acidic, and that's still basic. Okay, so I'm thinking I want to make this a little bit more acidic, so I'll dump in another 10 drops or so. And if you look at the side of this flask, you can now see solid formation occurring. Okay, massive amounts of solid are now forming in this flask, and that's kind of what I want to see, regardless of the pH change, because I've done this so many times, I kind of know what to expect. So let's test the, so it kind of looks like a pastel paint now. Test the pH paper. That's the lower little dot there. It's still showing it to be blue. Let's test the pH paper here. And that's still a little bit on the greenish side, okay? So I kind of want to see more of a yellowish kind of orange. I don't know what you call that color, okay? So I'm going to add another 10 drops here, and I'm noticing change here occurring. There's solid formation. That's the solid we want to precipitate. We want to make sure the phenoxide is sufficiently protonated and neutralized so that we get all of it when we do our filtration. So here goes 10 more drops. Okay. And the stir bar is stirring away in there while I'm adding that, so it's not locally hitting any one single part of the solution. All right, so let's grab our stir bar once again, test some pH paper. Okay. It looks a little green to me. Okay. Let's test the litmus paper. Okay. And that's still blue. Okay, blue. So I'm going to add 10 more drops here. We probably made a buffer, that's why there's not a lot of pH change here at the moment. So let's add 10 more drops and try to observe if there's any solid formation that occurs more. Okay, so that's another 10 drops. pH paper. Still looks kind of green there, which is right around pH 6 to 7, I would say. Okay. And this is showing a blue color right there, right above my finger is the blue color of the pH paper, of the litmus paper. Let's go ahead and add, it's a very thick solution now, suspension now, of a light tanned brown colored solid. Let's add 10 more drops. And I don't see a whole lot more solid precipitating here. It's pretty thick in there as it is. So I'm probably going to stop at this stage, but let's just check the pH paper here. Don't want to press my luck. Seems to be working, so I'm okay with that. All right. It's kind of a less, let me get more of a, it looks still green, but it looks more yellowish green. I'm going to just call it quits there. Let me test the the blue litmus paper. And this is still testing blue, okay, a little basic still. All right, so I'm going to go ahead and work this up. Now they suggest to gently evaporate the ethanol in some manner. I do not have a rotary evaporator, and I don't want to heat this up to evaporate ethanol. I've had bad things happen when I've heated the reaction mixture, all of this stuff up to try to drive the ethanol out. Since it's such a thick suspension, I'm just going to go ahead and filter it. So what I'm going to do is cool this in an ice bath for 10 minutes. Doesn't really matter if it's stirring here at the, in this. And then what I'm going to do is I'm going to perform a vacuum filtration. Then what I'm going to do is wash it with ice cold water from, this ice water bath a couple times to remove any salts. There's sodium iodide, sodium chloride, sodium thiosulfate, sodium sulfate, lots of stuff that could be down in here that's precipitating. And I want the water to wash all that inorganic stuff away so I have the pure organic substance to analyze at the end of this lab. So I'm going to stop the camera now, come back after 10 minutes, and then we'll do the vacuum filtration. Okay, we have our neutralized solution here. It's been cooled for 10 minutes, and we're going to go ahead and grab the ice water bath, the flask, and a dropper to add the water to the filtrated solid. So let's go ahead and do that now. So for the filtration, I'm going to use a water aspirator. When I turn the water on this hose here very rapidly, it pulls a vacuum through this sidearm flask here. So we'll attach our vacuum tubing, and of course I'm just using the filters here, 7 centimeters qualitative, and I've got my Buchner funnel with a rubber adapter. So jam that into the flask there, and because ethanol is the reaction solvent, which is soluble in water, miscible with water, I can just wet my filter paper with a little bit of water rather than ethanol, and cover it over the holes of the Buchner funnel. Yeah, so we'll get this started here, and we'll go ahead and filter our stuff. So it kind of looks like a thick suspension there, okay? Now when I filter, there is a magnetic stir bar in here. Sometimes people use a magnet and then they hold the flask in the palm of their hand, and then the magnet will keep the stir bar from falling in there. I don't really worry about that. I fish it out later at the end. So go ahead and turn this on. Okay, and I hear it. So I'll give this a swirl. Just pour that in there all at once, like so. And the stir bar has fallen in there, but I'm not too worried about that. I'll use a little bit of cold water from this ice bath here to rinse the flask and also the solid that is in there. So we'll wait for that to aspirate down. Let me try to move the camera here so we can take a better look at our substance. Okay, so again, you can rinse your flask just by squirting in some and then dumping it over there. And to rinse the solid, you don't want to just squirt liquid all on one side of the solid. You kind of want to dribble your water everywhere so that it has a chance to dissolve any water-soluble impurities. You don't want to add way too much because, of course, the product might be soluble to some extent in water. Okay, but we'll go ahead and do that there. One more time here. So we'll let that air dry. Basically let the vacuum pull air through the solids for a bit, and then I'll put this up in, out on the countertop for a day or two, and then we'll come back the next day and weigh it. I'll probably cover it with aluminum foil because the carbon-iodine bond is sufficiently weak to react with UV light. So I'll cover this with aluminum foil, but loosely, so that the water can still evaporate. Once this substance is dry, we can weigh it and get an accurate experimental yield, how many grams we've made. Okay. So there's not too much solid that's left behind on my magnetic stir bar, so I'm not going to worry about that. All right. All right, that's the product there, and we'll just go ahead and set this in a dark place to slowly dry, and then we'll scrape this off onto a watch glass and weigh it. All right. Now that we have the iodovanillin filtered and dried in this Buchner funnel, we want to transfer it to the balance and weigh the amount of mass for our yield. So I'll just zero out the balance with this watch glass on it, and we'll carefully take this out. It's kind of flaking off in these large kind of flakes, if you can see there in the video. So we'll eventually get this all on here and see what the mass is. It's like paint, flakes of paint. Of course, it's not the best technique to do this over the balance, Probably it's best to do it over the countertop and then transfer it, but that's what we're doing here today. The filter paper is fairly residue free. There's a bit of solid that's around the perimeter here, so let me keep working on that. Kind of has a faint tan color to it. Probably there are impurities present. Let's go ahead and position the camera over here so we can take a mass reading. So the crude solid weighs in at right there on the display, okay? So there's our substance. And we'll go ahead and analyze the crude substance for melting point now. All right, we're here with the melting point apparatus, and forgive my ignorance earlier, but 5-iodovanillin is supposed to have a light tan appearance, so this does indeed have that correct appearance. The literature melting point is provided in the research paper. I'll provide the link below, or you can log in through your institutional credentials and view the American Chemical Society publication. So we'll take a few bits of this and load it into a microcapillary melting point tube here. Let me put it into the melting point apparatus here and make sure we can see it well. Oh, very nice. Okay, so focus that again. All right, so that's what the solid looks like. Now I'm going to pull this out and crank the temperature up here to about 160 or so. Now if you look on the split screen here of the YouTube video, you can see me place the capillary in, and it's being magnified in there. It's within an aluminum block, and so we know this substance melts at around 170 to 190 or so if it's pure. I like to twist it around a little bit. That liquid looking thing on the bottom is the bottom of this glass little micro capillary, so that's not a liquid. Okay, so we're at 157 degrees Celsius here. Okay, and I like to twist it around to take a look at it. Sometimes when it heats up, it becomes more compact, which is what's happening now. I'm not quite sure if that's melting now or not. The good thing about the video is you could always replay it and reassess things and make a decision later on. So kind of just look compacting there. It's hard to tell. Don't think it's melting yet. With the color of the light and the magnification, it definitely does look like a tan color in there. Appears to be solid still. No change yet. So let me heat up the rate a little bit more. Almost looks like our substance is disappearing or subliming, perhaps. So now you can see it's beginning to melt. Do you see how the globules are beginning to fuse? That's why we call it fusion sometimes rather than melting. And it's just kind of disappearing there. You do see a small amount of substance on the bottom there, kind of coalescing and, you know, liquefying as it were. Okay, so looks like that might be the end. Changed to be a little bit more reddish. Okay, so that's the melting point range. All right, let's do that again. So we'll turn this down. Put more solid in there this time around, so we'll take a look at what happens. Becoming compacted. I would say that's when it's sweating or looking like it's getting wetted on the sides of the tube. It sure does appear to change in volume quite a bit. Alright, so you have to make the determination when you think it's fully melted there. A lot of little gas pockets and imperfections on the side of the glass that sometimes make that impossible to know for sure, but do your best. So that's the melting point of the crude 5-iodovanillin, and that's going to conclude the lab here. Thanks for watching.